MCEN 1131, Engineering Mechanics, Statics, Equilibrium Part 3, prepared by Mirko Dumanovic. Introduction. This is part 3 of our 3-part lecture on equilibrium. It is suggested you ensure your familiarity with the previous lesson, titled Equilibrium Part 2, before proceeding any further. This lesson will essentially be a continuation of the principles learned there. Two force members. A member that is acted upon by two forces, one on each end, for example, is known as a two-force member. A two-force member will always be in a state of either tension or compression. When a member is acted upon by at least three forces at several locations, there will likely be a bending in addition to compression or tension. The free body diagram for member BD from the previous slide can be drawn as shown in either figure 2A or 2B here. For BD to be in static equilibrium and not to rotate, forces B and D must be equal and opposite. Again, note that forces B and D are equal and opposite. Continuing from the previous figures, let us suppose that B subscript x is equal to 80 newtons. Knowing the slope of the member, we can apply trigonometry to solve for B subscript y as shown here. Using that, we can further solve for B. Thus, for two force members, the values obtained from one component can be used to solve for the unknown values in the other component, as well as the values of the total forces acting upon the member. In the free body diagram for member BD in figure 3A below, it is not necessary to show the horizontal and vertical force components at pinned connections B and D. Since member BD is in a state of only tension, the total force at B must have the same direction or line of action as member BD. If the line of action of force B had intersected with member BD at a different point, an unbalanced moment would have been present and there would not have been a state of static equilibrium. Notice how the forces at B, C, and D change direction depending on the member for which the free body diagram is drawn. This is because the forces depicted are internal forces and are equal and opposite to one another. Pulleys. Pulleys are simple machines that consist of a rope that slides around a disc called a block. Their main function is to change the direction of the tension force in a rope. Let us recall that the pulley systems that appear in physics almost always consist of idealized massless and frictionless pulleys, as well as idealized ropes that are also massless and don't stretch. These somewhat unrealistic assumptions mean three things. 1. The rope slides without resistance over the pulley so that the direction of the tension force is changed without impacting the magnitude of the tension force. 2. You can apply the law of energy conservation without worrying about the energy of the rope or the pulley. And 3. You don't have to factor in the mass of the pulley or rope when calculating the effect of a force exerted on an object attached to a pulley system. Consider the pulley shown on the right. There is a tension in the cable due to the 20.4 kilogram mass attached to it. We can calculate cable tension as 20.4 kilograms multiplied by 9.81 meters per second squared. This equals 200 newtons. The cable has the same tension throughout its length. Therefore, the free body diagram of the pulley will have two opposite forces of 200 newtons and horizontal and vertical component forces at point D. Note the horizontal and vertical components at point D. Adding the two 200 Newton forces vectorially, we obtain a resultant force of 179 newtons. To calculate the moment equilibrium about the center of the pulley, the resultant force R must pass through the center, as depicted in figure A below. Since R can be applied anywhere along its line of action, let us suppose that it acts at point D. Accordingly, we can resolve R into its original components so that there are two 200 Newton forces as depicted in figures B and C below. Coplanar concurrent force system. A coplanar concurrent force system has all forces on one plane intersecting at one point. In these systems, the free body diagram is usually illustrated on a point or pin. Consider example 4-8 on page 113 of the textbook. A horizontal beam with only vertical loading on it is an example of a force system in which all forces are parallel and on the same plane. In other words, it is a coplanar parallel system. The beam is supported at 2 points. The free body diagram replaces these supports with equivalent forces or reactions. Consider example 4-11 on page 117 of the textbook. Coplanar non-concurrent force system. When dealing with coplanar non-concurrent force systems, we are faced not only with vertical forces and moment equations, but also with horizontal forces, since the applied forces are no longer parallel. Pinned connections will now have horizontal components. Consider example 4-16 on page 123 of the textbook. Hints for problem solving. When drawing a free body diagram, remember the following. A. A free body diagram of a member shows forces acting on the member. B. Replace the support with an equivalent force acting on the member. C. Locate all points where the forces should be located. D. Show all of the forces and label each one. E. Show the slopes of forces if possible. F. Label all relevant distances. G. Cables cannot push and rollers cannot pull on a member. And H. Internal forces between connecting members switch directions when you are drawing the free body diagram for the different connecting members. Here are some additional hints. 2. For concurrent force systems, draw free body diagrams of only pins and points and not of the whole members. 3. For free body diagrams that result in simultaneous equations, the alternate solution is to use the vector triangle and sine law. This is often a shorthand solution. 4. If a pulley has been removed, the cable forces can be shown acting at the center of the pulley. 5. A two-force member that is in a state of compression pushes on the pins at each end. A two-force member that is in a state of tension pulls on each pin. The slope of the forces is the same as the slope of the member. Six. Assuming an incorrect force direction on the free body diagram will yield an answer with the correct magnitude, but one that will be negative. If you choose not to go back and change your solution to the corrected direction, you must use the negative answer as a negative value in any later calculation. 7. Check to be sure that you have not mistakenly switched the given slope of the members that you are analyzing. 8. Thoroughly check that the free body diagram is complete before beginning any calculations. And 9. When writing equations using the three equations of equilibrium, you may equate opposite forces or opposite moments rather than use the sign conventions that we've previously used. Homework. Read Chapter 4 up to page 113 and complete the practice examples and problems from the book as well as those provided by the instructor.